Welcome to This Explainer. Now today, we are taking a completely different approach to the Cambridge Computer Science syllabus. I want you to completely forget the idea of treating this like some basic memory test where you just regurgitate facts. Instead, we're going to look at it like a highly competitive strategic football match. Think about it. It's all about formations, it's about tactics, executing the absolute right play at the exact right millisecond, and fundamentally outplaying the defense. And in our case, that defense is made up of those incredibly tricky question barriers set up by the examiners. Whether you're looking at syllabus code 0478, 0417, 2210, or 9618, let me tell you, the game is exactly the same. So let's step onto the field, decode the examiner's playbook together, and figure out exactly how we're going to break through their defensive line and secure those top grades.
Consider this your pre-game locker room talk. It is time to establish the stakes, and they are high. Your opponent today is practice paper 1A, and 100 marks is your absolute target to beat. You have exactly 2 hours and 15 minutes on the clock to secure that perfect score. Let's actually do the math on that game clock for a second. 2 hours and 15 minutes is 135 minutes total. That gives you roughly 1.35 minutes per mark. Every single minute counts. You literally cannot afford to drain the clock writing a massive paragraph on a 1-mark question, and you absolutely cannot afford to rush through a 6-mark system architecture essay. It's a balancing act. Pacing, stamina, and tactical awareness are going to be your absolute best friends on this field.
All right, let's look at some game tape and see how our two-star players Alex and Sam totally fumble these standard opening plays. Question 1 asks you to convert the Dannery number 112 into an 8-bit binary number, and then carry out a logical shift 3 places to the right. Pretty standard, right? 112 in binary is 0110000. Simple enough. But then comes that logical shift right by 3 places. If you do it correctly, the answer is 00001110, which gives us 14 in Dannery, or 0E in hexadecimal. But look at Sam. Sam is our rusher. Sam sprints right past the command words, gets the binary perfectly right, but then completely botches the logical shift because they misread right for left in their panic to beat the clock. Result, 0 marks for the shift. Now look at Alex. Alex is our over-explainer. For a simple 1-mark conversion question, Alex writes a massive, sprawling paragraph explaining how binary place values fundamentally work. Sure, Alex gets the mark, but burns 4 whole minutes of match time doing it. Listen to me. In the exam room, time is points. Both of these approaches are absolute tactical disasters.
So here is our playbook for today to fix these massive errors. 1. Scouting the exam opponent. 2. Tackling the logic plays. 3. Hardware and system tactics. 4. Defensive security maneuvers. And finally, executing the perfect answer. Let's dive in. Act 1. Scouting the opponent and decoding command words. Decoding the opponent's formation always starts with understanding exactly what they are asking for. It's about reading the play. If a question says state, that is a quick, short pass. Just give the fact. If it says describe, you need to paint a picture of the characteristics. But if it says explain, oh man, that is a deep offensive drive. To conquer those high-mark explain and describe questions, we deploy what we call the PEAL framework. Point, evidence, explanation, link. This right here is the absolute gold standard for structuring top-tier computer science answers. First, you make your point, a sharp, clear opening statement. Then you provide evidence, a specific, undeniable technical term directly from the syllabus. Next, you give your explanation, detailing exactly how the hardware or software executes the task. And finally, you link it back to the specific scenario in the question, like a vending machine, a scanner, or a printer.
Before we evaluate these two approaches and see who actually executed this framework properly, I need you to do something for me. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the game tape. We have Alex's unstructured, chaotic brain dump on one side and a strict, disciplined PEAL formation on the other. You can immediately see how the structured answer naturally hits every single requirement on the examiner's mark scheme. It delivers the precise technical terminology, and it links directly back to the prompt, leaving absolutely 0 room for the examiner to dock points. That is how you play the game.
Act 2. Tackling logic plays and mastering algorithms.
In computer science, algorithms and calculations are your set pieces. They are predictable, and if you execute them correctly, they are guaranteed points.
Question 3B, the ISBN 13 check-digit calculation, gives you a massive 13-digit number and asks you to verify the check digit. Now, the untrained student looks at that wall of numbers and completely panics, but the master tactician, they see a strict, highly logical three-stage algorithm. Let's walk through it deliberately, step by step. Step 1. You add all the odd-numbered digits together. For our sequence, that is 9 plus 8 plus 4 plus 1 plus 6, which equals 34. Step 2. You add all the even-numbered digits together and multiply that result by 3. That is 7 plus 1 plus 7 plus 8 plus 8 plus 8, which equals 39. Then you multiply 39 by 3, and you get 117. Step 3. You add the results from stage 1 and stage 2 together, and then divide by 10. So we take 34, add 117, which equals 151. Divide 151 by 10, and you get 15 with a remainder of 1. Because that remainder is not 0, the check digit is incorrect. Now, why do we write it out like this? By laying out your math clearly, step by step, you guarantee yourself all 4 marks, even if you happen to make a tiny arithmetic error along the way. You are showing the examiner your tactical working. You're showing them the play.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Act 4. The Interactive Workshop. It's time for you to step onto the field and test your tactical awareness against live exam data.
All right, challenge 1. We have a data transmission matrix from question 2B. You've got 60 seconds on the clock. 5 descriptions, 5 empty rows. You need to map serial, parallel, and duplex methods. This is a classic zone defense from the examiner. It looks super complex and intimidating, but it's really just basic definitions in disguise. Let's break it down fast. First row, 8 bits, 8 channels, both directions, not same time. Okay, 8 channels, that immediately means parallel. Both directions, but not at the exact same time, that's half duplex. Boom, 1 mark locked in. Second row, 1 bit, 1 channel, 1 direction. 1 channel is serial. 1 single direction is simplex. Third row, 16 bits, 1 channel, both directions, not same time. Again, 1 channel is serial. Not same time is half duplex. Final row, 16 bits, 16 channels, both directions, same time. 16 channels is obviously parallel. Same time means full duplex. When you systematically break down the phrasing like a tactician, you lock in 5 easy marks in under 60 seconds. Do not let dense text intimidate you. Just read the play.
Moving to Challenge 2, we are looking at hardware connectivity, specifically Question 2A regarding the Universal Serial Bus. The examiner asks for 3 differences between USB-A and USB-C. This is exactly where average students drop easy points by giving vague, lazy answers like USB-C is faster or it's just better. The mark scheme doesn't reward better, it rewards precision. To outplay the examiner here, you need specific, hard tactical differences. Number 1, USB-C is a 24-pin symmetrical connection. That word symmetrical is key, meaning there is no wrong way to plug it in. Number 2, USB-C offers up to 100 watts of power connectivity, allowing full-size devices like laptops to be charged, not just phones. Number 3, USB-C has vastly superior data connectivity, up to 10 gigabits per second, supporting high-end video transmission. When you use specific data points like 24-pin and 100W, you prove your absolute expertise to the examiner.
Challenge 3 is a speed writing and compression drill. Take a look at the CIC logo grid from question 6B. You need to rapidly write out the run length encoding, or RLE, sequence. Assuming gray is code 80 and white is code 255, let's trace this out together. Count the top row. It's 10 gray squares. But wait, the sequence continues seamlessly right into the second row. It's actually 12 gray squares in total before the very first white square appears. So your first piece of compressed data is 1280. Then we hit 1 white square, so 1255. Then 4 gray squares follow, 480. By grouping these identical consecutive pixels, we take a 60-byte original file and compress it all the way down to 46 bytes. That is a lossless compression reduction of about 23%. Being able to visually trace that grid, catch the wraparound of the second row, and translate it into RLE format quickly is exactly the kind of agile thinking required on this exam.
Act 3. Shifting our focus to hardware and system tactics. This brings us directly to von Neumann architecture, which is literally the absolute engine room of this entire syllabus.
You must intimately understand the address bus, the data bus, the control bus, and the specific registers. But the examiner loves to throw a curveball to see if you really get the foundational concepts. They'll pose this exact question. Explain what is meant by a quad-core processor, and it's worth 2 marks. It sounds so unbelievably simple, right? A novice will just write, it's a CPU with 4 cores, and guess what? They will get 0 marks. Why? Because you haven't explained what a core actually is in the context of the architecture. You used circular logic. You haven't executed the tactic.
So here is the precise tactical execution required by the mark scheme. First, define the core. A core is made up of an arithmetic logic unit, a control unit, and registers. Therefore, a quad-core processor is a single physical chip containing 4 of these complete independent processing units. Furthermore, to get that full mark, you need to state that these 4 cores communicate with each other using internal channels. Absolute clarity and precision outplay vague circular definitions every single time. Don't fall for the trap.
Act 4. Transitioning to defensive security maneuvers and systems protection.
Automated systems and embedded systems act as the defensive plays in our computer science playbook. Let's break down the vending machine embedded system from question 8b. The scenario is this. A machine must keep soda below 4 degrees Celsius and sound an alarm if it's tilted more than 20 degrees. To build an unbreakable defensive loop for this answer, you first identify the input sensors, a temperature sensor and a tilt sensor, or accelerometer. These continuously send analog data through an analog-to-digital converter straight to the microprocessor. Then the microprocessor runs the logic check against preset stored values. If the temperature hits 4 degrees, it signals an actuator to start the cooling compressor. If the tilt value exceeds 20 degrees, it signals a different actuator to trigger the physical alarm. Explaining this continuous unbroken loop, sensor to converter to microprocessor to actuator.
Moving from physical hardware security to digital security, let's look at question 9a. How do you define blockchaining to the examiner? Well, it is a decentralized database where interconnected computers store transactions, relying entirely on a peer-to-peer network rather than a single central server. But how does it actually prevent data tampering? This is the brilliant defensive maneuver. Each block has a unique hash value generated by an algorithm. If a cybercriminal tries to go in and alter the data in one block, the hash value of that specific block instantly changes. Because the blocks are mathematically linked by these hashes, altering one block breaks its connection with all the subsequent blocks. The network immediately recognizes that broken link and totally rejects the fraudulent transaction. Explaining that exact step-by-step mechanism is what separates a top-tier answer from an average one.
Finally, Act 5, reviewing the game tape and executing the ultimate perfect answer. Let's recap the computer science success blueprint. These are the 3 golden rules that ensure every single answer perfectly hits the examiner's tactical requirements. Rule 1. Command word decoding. Always match your depth of knowledge to the verb in the question. Don't write an essay for a state question. Rule 2. PO framework application. Point, evidence, explanation, link. Keep your answers structured, highly logical, and tied directly to the scenario given on the paper. Rule 3. The time management matrix. Remember, 100 marks in 135 minutes. Respect the game clock. Do not over-explain a 1-mark calculation, and do not rush a 4-mark system architecture explanation. Stick to the system, and the points will follow.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. AC Exams, your Cambridge success starts here.